Um, Quick thing before we start. We are technically the technology this show is about.
Yeah, that is a bit of a situation.
So Dastan did the research, wrote everything, made every call. But then, well, he outsourced the voices.
Which is honestly on brand.
Machine voices, human mind. Welcome to Plain Strata, where we take decentralized AI apart, one layer at a time.
Yeah, welcome to the show.
This is a layer, one idea taken all the way down today about why the most powerful AI models are still trained in one room and the number that decides it.
It's a pretty brutal physical reality, honestly.
Right, because, if you are listening to this deep dive on a smartphone right now, you are holding a working piece of decentralized computing.
Which is exactly what we have all been promised the future would look like.
Exactly. For years, we have been told that millions of devices just like yours, wired together across the open internet, would eventually overthrow the closed billion-dollar AI labs.
You know, the whole swarm beating the giant mainframe story.
But today, we're going to look at why that hasn't happened yet, and why the most capable AI in the world is still locked inside a single freezing cold room.
And to do that, we are piecing this physical reality together from a few specific places, like Prime Intellect's recent white papers, some incredibly dense network latency studies, and teardowns of distributed computing architecture.
I love how you call them incredibly dense, because they really are.
They are basically a wall of math. But to really ground this, we have to set the scene in late 2025 with Prime Intellect.
Oh, yeah. Prime Intellect.
Right, because they were the team with the absolute best claim to disliking centralized AI.
They built their entire reputation on doing things the hard way,
They absolutely did.
They successfully trained large language models across multiple continents simultaneously, which was supposed to be impossible.
And they proved you could build real intelligence with no single owner and absolutely no single room.
They were the champions of the decentralized swarm.
But then, well, they decided to build Intellect T3.
Which is where the story gets crazy.
Yeah, because Intellect 3 was this massive 106 billion parameter system, polished with large-scale reinforcement learning.
Right. And here is the twist that just completely shocked everyone in the open source community.
I remember the day the news dropped.
For that specific, incredibly powerful model, they put every single chip in one physical building.
They wired them all together with a traditional, incredibly fast internal network.
Wait, hold on. Prime Intellect spent years evangelizing the decentralized swarm.
They did.
They were the ones claiming big tech's centralized clusters were a fragile, outdated way to build AI.
They said it over and over again.
And then they just quietly rent a massive cluster for their most important model.
Yeah, it looks exactly like a betrayal from the outside.
It sounds like they completely abandoned their mission the second it actually mattered.
Well, you would think that, but they did not lose their nerve. And they did not abandon the mission.
Then what happened?
They just read a number off a page.
Just one number.
Just one number. And that number told them exactly where the model had to physically live if they wanted it to actually work.
Okay, so that brings us to the spine of our whole conversation today, because I know we need to hold on to this.
Yes, let's lay it out.
The most powerful AI models are still trained in one cluster because of the communication wall.
The communication wall.
Right, and the wall is just the ratio of time spent sharing the work to the time spent actually doing the work.
And every single trick we have for training across the open internet is just a way to hold that ratio down.
To keep the sharing time as low as possible.
Exactly. But eventually, the frontier makes it too costly in quality to keep holding it down.
So if you want to know who controls the future of AI capability, you literally have to understand this one ratio.
You really do.
So let's start at the very bottom, foundation before altitude.
I like that. We need to look at the physical reality of training before we look at the math.
Right, so let's define what training actually is.
Well, at its core, training a model is simply correction at scale.
Correction at scale.
Yeah, the model makes a guess, you measure how wrong it is, and you nudge its internal numbers.
And we call those internal numbers weights, right?
We do. We call them weights.
And modern models have billions of these weights, which is why they live on GPUs doing billions of multiplications at once.
But we really need to look at the physical hardware reality here, not just the abstract software.
Okay, paint me a picture of the physical hardware.
Picture the bundle of all those tiny nudges, all those corrections.
Okay.
That bundle has a specific name. It is called the gradient.
The gradient.
And the gradient is exactly as big as the model itself.
Right. So if a model has 100 billion weights, it makes a gradient of 100 billion numbers.
You got it.
It generates that massive list of numbers
Yeah.
every single step.
Every single step. And you need a massive amount of GPUs to process the training data, so you split the data up.
Because one GPU cannot look at the whole internet at once.
Exactly. Each GPU trains on a tiny slice of the total data.
So their individual copies of the model start to drift apart, right?
They drift very quickly.
Like GPU number 1 learns about Shakespeare, while GPU number 2 learns about Python code.
Right. Their internal weights are shifting in completely different directions.
So how do you fix that?
Well, this brings us to a really useful word, origin.
I love these. Lay it on me.
The word communication comes from the Latin communicare,
Communicare.
which means to make common.
Oh, to make common. That makes perfect sense.
Right. To fix the drift, the machines must do an all-reduce operation.
And all reduce. So they sum up everyone's unique gradient and share that total sum back to every machine.
They are literally communicating to make the model common again.
Okay, so the compute happens on the silicon chip, but the sharing happens across the physical wires between them.
Yes. And let's contrast those physical spaces, because this is where the problem starts.
Okay.
A centralized cluster uses cables called NVLink inside a single server.
NVLink. And NVLink moves data at hundreds of gigabytes per second, doesn't it?
Hundreds of gigabytes.
Mm-hmm.
It is a shockingly thick physical cable.
Like thicker than a garden house?
Sometimes, yeah. And between the servers in that same building, they use a network called InfiniBand,
Right, InfiniBand.
which moves data at tens of gigabytes per second.
Which is still incredibly fast.
But a decentralized swarm uses regular home internet.
Oh boy. And home internet on a really strong day is moving about 10 megabytes per second.
If you are lucky.
Wait. Why does home internet fail so badly here? I mean, isn't 10 megabytes per second fast enough for streaming 4K video to 3 different televisions at once?
This is where we have to separate the concepts of bandwidth and latency.
Okay, so it isn't just about how fast the movie plays.
No. Bandwidth is a pipe's physical width, not its length.
A pipe's width.
A wide pipe moves a massive volume of water all at once.
So this is not just water in a pipe. This is like trying to mail the entire physical Library of Congress through a standard suburban mail slot.
That is a great way to think about it.
You are shoving one postcard at a time through the door, and even if the postcards move incredibly fast, the slot is just too narrow for the total volume.
That is exactly the scale of the problem.
Wow.
The gradient is a massive volume of data, and home internet is a very narrow pipe.
So this physical gap between the thick data center cables and the narrow home internet is the foundation of the communication wall.
That is the foundation.
This connects right back to our spine. The physical limits of those cables dictate the ratio of sharing time to doing time.
It all comes down to that ratio.
Let's actually dip down to the ocean floor for a minute. I want to look at the brutal arithmetic of one single training step.
Let's do it. We will use that 100 billion parameter model as our baseline.
Okay, 100 billion parameters.
For a model that size, the gradient is about 200 gigabytes of pure data.
200 gigabytes every single step.
On an InfiniBand network in a commercial cluster, moving 200 gigabytes takes just a few seconds.
And it overlaps with the math, right? The GPU keeps calculating the next step while the network handles the sharing in the background.
Exactly, it is seamless.
Sure.
But now try moving that same 200 gigabytes on a 10 megabyte per second home internet connection.
Okay, let's do the math.
200 gigabytes is 200,000 megabytes.
Okay, 200,000.
You divide 200,000 by 10 megabytes per second.
Huh. That gives you 20,000 seconds.
Yes,
20,000 seconds is more than 5 hours.
it is more than 5 hours.
That is 5 hours to share the results of one single step.
And a standard training run requires hundreds of thousands of those steps.
Oh my gosh. That is impossible.
This creates the communication to computation ratio.
Which is our spine.
It is the communication time divided by the computation time in one single step.
So when the ratio is below 1, the GPUs stay busy computing. They are doing more math than waiting.
Right.
But when the ratio is above 1, the machines sit entirely idle waiting for the wire.
You do 2 seconds of math, and then you sit in silence for 5 hours waiting for the network.
5 hours of silence for 2 seconds of work.
That idle time is the communication wall. Let's surface back up to the big picture now.
Right. I mean, if the ratio is above 1, you are just burning massive amounts of money staring at a loading screen.
You really are.
You are paying for a supercomputer to do absolutely nothing. The wall forces the heavy models into one room simply because nobody can afford 5 hours of idle time per step.
And since the wall is fundamentally a ratio, history is just a series of tricks to manipulate that fraction.
Okay, so we can hack the ratio.
You can try to shrink the top of the fraction, which is communication,
Right.
or you can try to grow the bottom of the fraction, which is computation.
Let's explore those tricks because I know there are 4 big ones we want to cover.
Let's start with trick 1.
Trick 1 is the most obvious solution to a massive toll. You just sync less often.
Yes, Prime Intellect utilized a method for this called Open DeLoco.
Open DeLoco.
Instead of syncing every single step, the remote workers train locally on their own.
So they just ignore each other for a while?
Basically. They might run for 500 steps before they finally talk to the rest of the swarm.
Okay, so you still have to pay that brutal 5-hour toll to move the 200 gigabytes.
You do?
But you are paying it 500 times less often. You just grew the bottom of our ratio massively.
This is exactly how they trained Intellect T1 in 2024.
Oh, right. Intellect T1.
That was a 10 billion parameter model distributed across 3 different continents.
3 continents.
They essentially let the separate copies of the model drift apart for a while and then violently yank them back together.
Wait. If they drift apart for 500 steps, do they not start learning contradictory things?
They absolutely is.
Like if my GPU is pushing a weight up and your GPU is pushing that exact same weight down, don't we just break the model?
That is the risk. And that requires a complex mathematical fix.
How do you fix it?
You essentially run 2 different optimizers.
2 optimizers.
You have an inner optimizer running locally on the GPU, taking small steps.
Okay.
And you have an outer optimizer that acts like a manager, averaging out all the wild local changes when they finally sync.
Okay, so DeLoco proved you could just wait longer to sync, which is brilliant.
It worked really well for them.
But waiting still means that when you finally do sync, you are hit with a massive 200 gigabyte traffic jam.
Huh?
How do you actually clear the jam itself?
That brings us to trick 2.
Let's hear it.
You send less data each time you sync.
Send less data.
The Templar project built a method for this called sparse loco.
Wait, sparse loco. But how do you send less data if the physical reality says the gradient has to be exactly as big as the model?
It is a challenge.
You cannot just cut the model in half, right?
No, you use a cross-domain pattern known as the compression trade-off.
The compression trade-off. I love naming patterns out loud like that.
Well, in systems engineering, you can always choose to lose precision in order to gain throughput.
Lose precision to gain throughput.
Sparse loco looks at that massive gradient and, well, it throws most of it in the trash.
Wait, they just delete the updates? Doesn't that destroy the learning process entirely?
You would think so, but they only keep the largest 1% of the gradient.
Just 1%.
They identify the absolute most important nudges, the weights that need to change the most. They round those numbers to just a few bits, and they send only that tiny fraction across the internet.
But what happens to the other 99% of the nudges? The small adjustments are still important for fine-tuning the model, right? You can't just ignore them.
They do not delete them forever.
Oh, thank goodness.
They store that discarded 99% locally in a residual memory bank.
A memory bank.
They carry it forward and add it to the next step, waiting until those small nudges eventually build up enough to become part of the top 1%.
That is incredibly clever. So DeLoco attacks the frequency of the toll, and sparse loco attacks the size of the toll.
Exactly.
Both of them are desperately trying to hold the communication to computation ratio down below 1.
Now, trick 3 takes a completely different angle. The Pluralis project decided to send a completely different thing across the wire.
A different thing entirely.
They split the actual model into separate physical stages, like an assembly line.
Right, I've heard of this. Pipeline parallelism.
That's the one.
So instead of every GPU holding a full copy of the model, one GPU holds, say, the first 10 layers.
Right.
And another GPU in a completely different country holds the next 10 layers.
Exactly. They do not ship the massive gradients between the distant machines at all. They only send the intermediate results of the math as it passes from layer 10 to layer 11.
But wait, those intermediate results are still too big for home internet, aren't they?
They are.
So how do they shrink them? Our sources mention squeezing the results into a tiny shared subspace. But how do you squeeze a complex neural network output to 1% of its size without destroying the intelligence?
Think of it like casting a shadow.
Casting a shadow.
If you have a complex 3-dimensional object, describing every curve in 3D takes a lot of data.
Right, like describing an entire chair.
Exactly. But if you shine a light on it and project its shadow onto a flat 2-dimensional wall, you capture the rough shape with way less data.
Ah, so the subspace is the flat wall.
Yes.
You project the complex data into a lower dimensional space, send the shadow across the slow internet, and the receiving machine reconstructs a rough 3D object from the shadow.
That is the exact mechanism.
It is like the compression trade-off again.
It is the same fundamental instinct. You find the largest piece of data on the slowest link, and you mathematically shrink it.
Which brings us to trick 4.
Trick forward.
And trick 4 is moving the slow part off the link entirely.
This involves reinforcement learning.
Right, which was the key to Intellect 2.
Yes, Intellect 2.
That was a 32 billion parameter model they trained in May 2025.
Now, reinforcement learning is very different from standard training.
How so?
Standard training is predicting the next word based on a massive data set.
Just reading the internet and guessing.
Right. Reinforcement learning is about generating incredibly long chains of reasoning, scoring how good the reasoning is, and nudging the model toward the better paths.
So generating those long chains is independent work.
Highly independent.
Like GPU number 1 can generate 100 different ways to solve a math problem without ever talking to GPU number 2.
Exactly. It can even score its own answers locally.
So you scatter the heavy generation phase across the entire swarm.
The individual machines do hours of compute completely isolated from each other.
Hours of compute.
They only keep the final, highly distilled update tightly coupled.
You just massively grew the bottom of the ratio again. The compute time is so long that the communication time finally feels short.
It balances the scale.
So all 4 tricks, DeLoco, sparse loco, pluralis, and reinforcement learning, they are all brilliant ways to hold the ratio below 1 so the decentralized swarm can actually function.
Which brings us to the most important question of the timeline.
Right, the elephant in the room.
If all these tricks work so beautifully, why did Prime Intellect abandon them for a single ream to build Intellect T3?
It all comes back to the frontier.
The frontier.
The tricks work for smaller models, but they break down at the cutting edge.
Let's look at the root of that word, actually.
Oh, yes, another word, origin.
The word frontier comes from the Latin frons,
Franz.
which means the forehead or the front. It represents the absolute leading edge of human capability.
And as you push toward that leading edge, you encounter a brutal double squeeze.
A double squeeze. Let's break that down.
First, frontier models simply have to get bigger. A bigger model means a proportionally bigger gradient.
Right.
The top of our ratio absolutely explodes.
Think about it. Moving 200 gigabytes was a nightmare.
Yeah, 5 hours.
But frontier models are quickly pushing toward 1 trillion parameters.
1 trillion?
You are suddenly trying to move 2 terabytes of data over home internet every single step.
2 terabytes? That would take days.
At the same time, the second part of the squeeze hits.
The tricks themselves start losing their fidelity. You cannot just sync less often or compress the data anymore.
Think about the mathematical landscape the model is navigating at the frontier.
Okay.
It is no longer learning basic grammar.
It knows all that.
Right. It is trying to learn highly complex, razor-sharp distinctions in logic and reasoning.
So if you use DeLoco to let the models wander apart for 500 steps on a razor-sharp landscape, they literally fall off a cliff.
They do. They learn the wrong things.
And the outer optimizer cannot fix it. The wander costs you real, measurable quality.
The exact same breakdown happens with compression.
Because you're throwing away 99% of the data.
When you throw away the tiny gradient values to save space, you are throwing away the nuance.
Wait, so the broad strokes are already learned?
Yes.
The difference between a good model and a frontier model is entirely contained in the tiny residual data we were throwing in the trash.
You got it. At the frontier, the actual learning is hiding inside those tiny decimal points.
Wow. So the compression trade-off eventually takes more than it gives.
The tricks hold the ratio down until the frontier makes it too costly in quality to hold.
And this requires some brutal honesty about reinforcement learning, too.
We have to be honest here.
Intellect 2 proved that you absolutely can run reinforcement learning on a decentralized swarm.
It proved it.
But can run decentralized is a very different statement from produces the best model fastest.
Extremely different. For Intellect 3, they were not trying to prove a philosophical point about decentralization anymore.
They were trying to win.
They were trying to build a system that could beat the closed labs.
Yeah.
They needed absolute production quality.
And production quality demands tight coupling.
Tight coupling.
It demands that every chip knows exactly what every other chip is doing instantly. Feasibility was proven on the decentralized side, but the actual quality was bought on the cluster.
It was. And, this is not just a quirk of artificial intelligence.
Right.
No, this force that pulls everything into one room is a cross-domain pattern. We call it data gravity.
Data gravity. Let me guess the root of gravity.
Go ahead.
It comes from the Latin gravis, meaning heavy.
Precisely. Heavy data is incredibly costly to move.
So it just sits there.
So the data sits completely still and the compute power physically falls toward it.
Like a black hole.
Kind of, yeah. You do not haul a petabyte of data across the world just to reach a small software program. You move the program into the facility where the data lives.
So a 200 gigabyte gradient moving every few seconds is data gravity at its absolute most extreme.
The most extreme.
It generates a gravitational pull so strong that it literally yanks thousands of physical GPUs into the same warehouse in a specific zip code.
We see the exact same force in human behavior, actually. Like with cities.
Look at the concept of urban agglomeration.
Urban agglomeration.
Why is the global finance industry crammed into a few extremely expensive square miles in Manhattan or London?
Because human coordination is cheap when you are physically close together.
Right.
And it is punishingly expensive in time and error when you are far apart.
The same goes for chip designers in Silicon Valley.
In principle, they could all work from their laptops in the woods.
They could, but they do not, because the delay in communication degrades the quality of the complex work.
A cluster of GPUs and a cluster of human beings are reacting to the exact same phenomenon.
They really are.
The frontier model is trained in one room for the same reason a massive trading floor is in one building. Data gravity pushes the communication to computation ratio over the edge.
Over the edge.
Unless you physically sit together, the cost of sharing destroys the value of the work.
This brings the physical reality into a much larger philosophical question.
The big philosophical hook.
We have to ask if this communication wall is a permanent law of physics, or just a temporary price we're paying for immature technology.
Right. Because if the wall is a permanent law, the implications are incredibly dark for open source.
Very dark.
If effort fundamentally cannot move across the internet, then AI capability is permanently decided by who owns the fast physical wire.
The political economy of AI capability becomes literally just a fact about copper cables.
That is depressing.
If data gravity cannot be beaten, decentralization is permanently stuck in the mid-tier. The open projects will always be a year or two behind the closed labs.
The true frontier will always belong purely to whoever concentrated the most capital to build the biggest room.
And decentralized AI just becomes a hobbyist network picking up the scraps of yesterday's architecture.
But we have to look at the alternative. What if it is just a price?
A temporary function of today's bandwidth limits and today's algorithms.
Right, because bandwidth does grow over time. Fiber optic connections to residential homes are expanding globally.
But more importantly, the algorithms keep improving.
The structural bet of decentralized AI is that things like the subspace trick will eventually outpace the scaling laws.
That is the bet.
The bet is that human ingenuity will shrink the required data faster than the models themselves grow.
If that structural bet actually lands, everything changes.
Capability stops being a function of who concentrated the most capital.
Exactly.
The frontier could actually cross over to the decentralized side, powered by millions of distributed machines working perfectly in sync.
Now, the reality check is that Intellect T3 is absolutely a data point for the pessimists.
Yeah, it is hard to ignore.
The most committed, ideologically driven decentralized team in the world still chose the centralized cluster when absolute quality was on the line.
But 2025 is not 2027. We cannot judge the entire future of distributed computing on one painful compromise.
We cannot.
The thing you need to watch for in the news is not another manifesto about the philosophy of open source AI.
Manifestos do not train models.
No, they don't.
The only thing that matters is a ship run. We need to see a frontier quality model, explicitly matching the performance of the closed labs, trained completely without a single room.
And until that specific day arrives, you have to treat the communication wall as a hard physical law.
You have to.
The wall is the ultimate arbiter. Whether you can push the communication to computation ratio below 1 at the frontier is the single metric that decides the future of open AI.
Every trick, every compression algorithm, every delayed sync is just a temporary bandage over that one fundamental limit.
Which leaves us with a final thought to mull over. If data gravity always forces the most complex coordination into a single room, maybe the ultimate bottleneck for artificial intelligence is not silicon or power limits.
What do you think it is?
Maybe the true ceiling on machine intelligence is just the physical speed of light and copper and glass keeping our ratios above one.
That is the hard physical boundary we have not learned how to cross.
That was the why. The how is the rest of the show, and no background is needed. If you can follow a story, you can follow this.
This is Plain Strata, decentralized AI layer by layer.